Hello everyone, my name is Dr. Vile. Welcome to my YouTube channel. The purpose of this YouTube channel is all about getting you ready for your A-level chemistry exams. And with that in mind, this video is going to be looking at how we do calculations involving frequency, wavelength and energy. If you find the video helpful, remember to like, subscribe and share with your friends. Keep checking back for more content. Okay, so in terms of these calculations, there's two formulae that you need to know. Hopefully they ring some bells. The first one is E, which is energy, equals H times, I'll just call it F because it's easier to remember when we think of that. So E is energy, and it would be measured in joules. What does H stand for? Have a look on your data sheet if not. There should be a piece of data on your data sheet that tells you what H is. It's called Planck's constant. And that is 6.63 times 10 to the minus 34. And the units for Planck's constant are joules times seconds. So F stands for frequency. Now frequency is measured in hertz, but hertz simply mean per second, because it's the number of things per second. So when you look at the units here, you've got joules, seconds, and seconds to the minus 1. So the seconds and the seconds to the minus 1 just cancel out, hence why you end up with joules as the units for energy. Okay? So that's the first formula that you need to know. The second formula that you need to know is C equals F times lambda. Do these ring some bells at all? What does C stand for on your data sheet? Sixth one down. I'm very shy. Speed of light. Yeah? So C is the speed of light in a vacuum. And it's 3.00 times 10 to the power of 8, and that's meters per second because it's speed. F once again stands for frequency, which is measured in seconds to the minus 1. And lambda, what does lambda mean? Ends with a W. WA, wavelength. Yeah, I know what it is. No one wants to say anything because you know it's being recorded. Wavelength is measured in meters. Okay. So these two equations we need to know. We've got E equals H times F and C equals F times lambda. They can be combined together where we insert, if we think F equals C over lambda, if I just rearrange it, we could then write that E equals H times C over lambda, so we can combine them together. And what that means is we can convert straight from wavelength into energy, or straight from energy into wavelength. So these are the formulae that we're going to need to use to solve problems, but we need to make sure that we're using the correct units when we use them as well. So you've got red light has a wavelength of 650 nm. Now N means nano. If you look on your data sheet, can you see at the bottom you've got this little table with multiple prefix and symbol? Well, the N stands for nano, and it means 10 to the minus 9 on your calculator. So what this means is 650 nanometers is the same as 650 times 10 to the minus 9 meters. And to go into our equation, it needs to be in meters, not in nanometers. So we have to convert from nanometers into meters. Okay. So we know the wavelength. And if we think back to the previous page, I said that E equals H times C over lambda when you combine the two equations together. H and C, you just look up on your data sheet. They're just constants. And lambda is what we've just worked out here, the wavelength. So if we plug the numbers into our calculator now, you'd have H as 6.63 times 10 to the minus 34 times C, which is 3.00 times 10 to the power of 8. And then we divide that by lambda, which is our 650 times 10 to the minus 9. So when I put that into the calculator, I get it as 3.06 times 10 to the minus 19. Now, because we put everything in the right units, it's going to come out in joules, which is right, but we need to answer the question. And the question wants it in kilojoules per mole. So we're going to have to do 2 steps to convert it from joules to kilojoules per mole. Firstly, convert to kilojoules. There's 1,000 joules in a kilojoule, so we divide this number by 1,000. And that'll put it into kilojoules. Come on.
I was waiting until 2 minutes, for 20 minutes, so I thought I'd just go.
Oh, there we go. Come on in. So yeah, that comes out as 3.06 times 10 to the minus 22 kilojoules. So on your data sheet, you're also told that Avogadro's number, Na, can you find that one on the data sheet? Is 6.02 times 10 to the power of 23, and that is moles to the minus 1. So what that means is if you have a mole of something, it has 6.02 times 10 to the power of 23 atoms in it. Well, if you look at the units, this is kilojoules, and this is moles to the minus 1. So if you multiply them together, your units will come out in kilojoules per mole, which is what we need it to be. So you take this 3.06 times 10 to the minus 22, you times it by Avogadro's number, and that'll give you your answer in kilojoules per mole. And I get that to be, to 3 significant figures, 184 kilojoules per mole. Yeah, so the frequency is 450 gigahertz. That is the same as 450 times 10 to the power of 9 hertz. We've just taken the gigabit out and replaced it with times 10 to the power of 9. So that is your frequency. And then we know that E equals H times F, where F is the frequency. So H is on your data sheet. It's just 6.63 times 10 to the minus 34. F is what we've just said here, 450 times 10 to the power of 9. And when you chuck that all into your calculator to 3 significant figures, that comes out as 2.98 times 10 to the minus 22. And that'll be in joules, which is the standard unit of energy, assuming you put everything into the calculator in the right units to start with. Now, I've written 2.98 times 10 to the minus 22 joules. I would leave it in your calculator because there's actually more significant figures than that. I'd round it at the very end, but leave it in your calculator. To go from joules to kilojoules, we divide by 1,000. So that would be 2.98 times 10 to the minus 25 kilojoules. And then to go from kilojoules to kilojoules per mole, just like we did on the previous example, you times that by Avogadro's number, Na. Which comes out as 0.18 kilojoules per mole. So relatively low energy. Is everyone okay with what I've done there? So it also said, that is only the first part of the question. This is a double whammy just to practice the skills, really. The second bit says calculate its wavelength. So we know that E equals H times C over lambda. Although actually I think we can use a simpler version of this rather than doing this. We can simply say, because we know that C equals F times lambda, I think that's the easiest way to approach this. Using this one, C equals frequency times wavelength. And therefore, if we're trying to find out wavelength, we divide both sides of the equation by frequency. So it becomes C divided by F. That will make life nice and easy now, I think. So C is the speed of light, which is 3.00 times 10 to the power of 8. And the frequency we said was 450 gigahertz, which is 450 times 10 to the power of 9 hertz. Now, it might be worth putting the units in here to show you how this works, because speed is in meters per second, and frequency is now in per second. So when you bring the per second up to the top, it becomes seconds, which cancels out with the seconds to the minus 1, so you just get left with meters as your units, which is what you want for wavelength. Wavelength needs to be in meters. So we chuck all that into your calculator, and that comes out as 6 times 10 to the minus 4 meters. Okay, so light's got this energy of 4.67 times 10 to the minus 19. Calculate the wavelength. Well, we know that E equals H times C over lambda. So that's the formula that links energy and wavelength. It's the combined of the two equations. And therefore lambda, which we want to calculate, the wavelength, is equal to H times C divided by E. Just rearranged it to make lambda the subject of the equation. So what we'll do is we'll plug all the numbers in, making sure we get the units right. So H is 6.63 times 10 to the minus 34. The speed of light is 3 times 10 to the power of 8. And then the energy in joules is 4.67 times 10 to the minus 19. And that comes out as 4.28 times 10 to the minus 7 meters. Now, I've not quite answered the question yet, because we need to put it into nanometers. Well, we know that 1 nanometer is the same as 1 times 10 to the minus 9 meters. That's what a nanometer means, 1/1000th of a meter. So what we do is we take this number here and we divide it by 1 times 10 to the minus 9 to put it into nanometers. And that comes out as 428 nanometers. Now 428 nanometers is short wavelength. It's the short end of visible light, which means it's high energy visible light, which probably means it's violet light. If you look at I'd have to pull up a picture of the electromagnetic spectrum to show this, but it's the low end in terms of wavelength, which means it's high energy, and high energy is probably violet light. Do you remember Richard of York gave battle in vain, red, orange, yellow, green, blue, indigo, violet, the way to remember the colours of the rainbow in the order that they're in? No? No? Anyway, 428 nanometers. Anyway, thank you for taking the time to watch this video. If you found it helpful, remember to subscribe to the YouTube channel, to like it, share with your friends, and keep checking back for more content as this channel is updated regularly. Thanks everyone, see you next time.